And welcome back to the Coleman LED lamp conversion to lithium part 2, the power control circuit. So let's think about how we can control the LED brightness without just using current limiting resistors as shown here. There will be a better way, but it will be more expensive to do. So we can see why the manufacturer chose the cheaper option at our expense of wasted energy dissipated in the resistors. So let's have a look at an NE555 timer. Let's have a look at some pure hardware solution. The NE555 timer. Now everyone's used it for doing lots of things, making oscillators and that. And it's got a very simple schematic of how it works. But there is a pin called cont. And that can be used for altering the biasing chain down here. And if we zoom down, wow, whizzing down fast here now. Past the different versions of it, and eventually we will come to pulse width modulation. And here you can see they have a timing network here, and then they have a modulation input onto this cont control, and by changing the voltage on here you can change the way this bit works in a kind of pulse width modulated way. It goes through telling you how to do it, and then it gives you a circuit of some waveforms down here, and they've got an AC input voltage, and as you can see the output voltage is sort of varying in pulses. Now the problem is the pulses don't seem to change a terrific amount, and the gaps do a little bit, but it's not kind of how I'd want to do the pulse width modulation. I want more control over it, and this doesn't look like it's going to give it to me, so I discounted that and didn't even bother going any further than looking at the data sheet. So I started to have a look at a more hardware and firmware solution using an Arduino, or in this case an Arduino AT13 or ATTiny-13, because it's an 8-pin chip, and it has all that we need. It has digital inputs for the monitoring of the power state required, and a PWM output that's quite easy to drive. And this gives us a pro points that we can figure the PWM signal to provide the two brightness levels, and we can decide on how much current we want and things like that. And we could add extra functions like flashing to warn of a low battery voltage, etc. And so it's quite flexible. The negatives is, of course, the batteries power the LED directly, and so as the battery voltage reduces, this is going to keep the PWM constant, and so the voltage across the LED is effectively going to decrease, and so the LED will get dimmer. And so a fully charged battery, it'll be nice and bright, and an almost flat battery, it's going to be a lot dimmer. So that paid to using the ATTiny as my solution. As you can see, I also did a bit of filtering on the supply to keep it away from the kind of pulsing of the LED, but it didn't quite live up to how I wanted it to work, and so again that design landed on the toy room floor. Now this circuit is like the hardware take two, and the idea is to use a buck boost converter to drive the LEDs. The TPS 63802 is designed to run off lithium batteries, so its input range kind of matches a single lithium battery, whereas I'm going to have 3 of them in parallel. As I got 3 batteries because originally I thought that the LED was running off 12 volts, so we're going to stick them in parallel, give us a nice current supply, and then this will boost the voltage to 3 volts when the batteries are lower, and it will buck down the voltage LEDs when of course the voltage is above the 3 volts the LED needs. And the feedback is a 500 millivolt level signal, and so basically when that point reaches 500 millivolts with reference to the grounds, then it will stop. It will keep that output level constant. It will stop changing it. And so for the high power option, we have two resistors in parallel, so it draws about 800 milliamps to get to the 0.5 volts. And then in the low power R14, this one here is switched out, this one's left in, and so of course less current is needed to increase the voltage across that resistor to 500 millivolts, and so that provides the low power option. But it's still not brilliant, because even 800 milliamps across 1.67 ohms resistor is still a watt or so. Well, it's across those two, so it's going to be less than an ohm, so it's going to be more than, it's a watt shared between the two of them. And at 300 milliamps across the 1.67, it's going to be about 400 milliwatts, something like that. I have not bothered calculating it. So this circuit allows you to keep the brightness constant as the battery voltage changes, but it's still relatively inefficient, because we're still dissipating power in these two sense resistors because they're reasonably high values. So that kind of prompted where I'm going, but again it fell on the toy room floor. Right, this is hardware version, the final cut, so to speak. As you can see, it resembles closely the buck boost circuit you saw just now, only the area around here has changed. Instead of having the switching down here, it's now up here. And what this is doing is, you've still got the same 500 millivolts feedback voltage, but of course you've got a 0.2 ohm resistor, which in the final circuit is higher. It's about 0.36, because that's the value I found laying around before I could find a 2.2. So I just played around and changed the values accordingly. And how this circuit works is, the chip is going to try and output the voltage until it gets the 500 millivolt reference back, and then it stops at that when that's achieved. Now, to get 500 millivolts across 0.2 of an ohm, that's quite a lot of current, which means it will burn the LED out. But as you can see, we've got a 56 ohm resistor here, and what we're doing is through in the low power section, we're coming down here through the switch, through the resistor here, and we're also going down through here. So the current's flowing down these two resistors through the 56 and down here, and so the voltage across here adds up to 500 millivolts. And so we are effectively controlling the current down here by controlling the voltage across the 56 ohm resistor. So the more voltage we drop across here, the less current is going to be flowing down here from the LED, because this is going to shut off earlier. And so when we go into the high power mode, we take this resistor out of circuit, and so now it's going to increase in value here. So a larger value here means less current down here, which means to make up for less current flowing through here, so less voltage drop across R56. The voltage will increase, so more current flows down here. This makes up the difference. And so what happens is, with these two in parallel, the voltage across here is enough so that there is only 300 milliamps flowing down here. And then when we take this one out of circuit, the current drops, and so the current through here goes up to about 800 milliamps in order to achieve the 500 millivolts in the feedback loop. And that's how it works. And as before, as the batteries change in voltage from 4.2 down to say 3, at 4.2 we're in buck mode, because we're getting about 3 volts across here, and when it gets down to about 3 volts, then we go into boost mode to keep the 3 volts across here. And so the brightness is much more consistent. The only difference is, as the batteries go down in voltage, the current they draw, or the current they supply, will increase, because the power is going to stay, the power is trying to stay the same here. And so less voltage, more current, more voltage, less current. And that's the final circuit. That's the one we're going to sort of build up, and we're going to throw in a charger board and a battery protection board, well, 2-in-1 board. We'll throw that in as well. Well, this is the board I bought off AliExpress. You can just search for them for TPS 63802 and you'll find loads of people selling them, so I won't link a description for it. Here's a quick picture showing all the components that I'm going to remove so that I can use it with my circuit. This picture here shows the board with all the components not needed removed, and little and where I'm going to put my new components is highlighted in red. So what I'm going to do now, I'm going to solder. This is just a mock-up to see if it works. It might not. I've got 4 of these little units to play with. And a bit of solder on them's not going to hurt, is it? So LED on there. There's a tweezer somewhere. Sense resistor on there. Bit of tin copper wire. This is quite old tin copper wire. I don't know how well it's going to solder. He says moving that right out of the way so you can't see it. This is a 5-watt LED, so let's see how warm it gets. Probably old tin copper wire. It oxidises. And when it oxidises, you can't solder to it very well. So I'll bend that down there. And then like that. Okay, there. This is just sort of rat's nesting, just to see if the idea works. Problem is now I need to go and find some resistors. So you're going to have to bear with me. Oh, these are some very old resistors, as you can tell by they come from Proop's electrical shop in Lower Addiscombe Road, Croydon. These must have been 40 years old more by now, maybe even older. And I've been using these resistors on and off for a long time. I rat's nest them and then put them back when I don't need them anymore. So, soldering iron, where'd it go? Over there. Ooh, sticky feet. So this is going to be the feedback for VREF. Stick down there. Go on. Ouch, it's getting hot, right. And I can't find the values I want, so I'm going to use an 820. So lowering the value of the resistor will lower the output current. That might surprise you. Lowering the value of the resistor lowers the output current. And this one is going to go from V out and it's going to turn around. Ouch, it's hot. I'll do my best so that I don't have to cut the wires. Poof. Join those together. And now I need a little bit of this trusted wire. Because I have to pick up pin, a tiny little pad. It's the problem with using these boards that someone else has made. As they've used really silly small components. I might have to put a magnifying glass on so I can see what I'm doing. I could use the scope, but that gets in the way. Now you're probably going to see the back of my head. Not sure, but I'm going to have to get pretty damn close. Right, I don't know if you saw the back of my head, but that wire's on. I think if this actually works, I might send off and get a board made, buy some of the chips, rather than trying to bodge this every time. Right. Can we see it? So there it is. I have the diode LED going from out down to ground via a 0.36 ohm resistor. I have a 56 ohm resistor coming down to here. I have an 820 ohm resistor back up to there, and then this point is going down to the reference for the chip. So, will it go bang? So power supply set to 1 volt. Put it on here, onto here. Turn the output on. Whoa! Wow! 2.2 volts. I'm going to put a bit of tissue over here, just so that it covers the light up. It's a bit bright. We'll put power on. This is running at 3.2 volts going in. You can see how bright it is, and that's pulling 0.6 of an amp. That's with 1k in parallel with the 800. So if I want to go lower, then what I can do is put it up to 9, drop that, and then you'll see we're at half an amp now, or 5.4 amps. Go down another notch. We're getting dimmer. As you can see, as I lower the current, lower the resistor value, we drop down, and now we're at about 300 milliamps. Drop it again, about 255, go up a couple, knock it up to 300, say. There you go, with 540 ohms in parallel with the 820, we're running at about 300 milliamps, and if I remove that, that is bright. If you're enjoying it so far, click on the subscribe button, click on the like button, and click on the bell for notifications, and I'll catch you on the next one.